My name is Logan Hauser.
And my name is Bazini.
We are the developers of the
Solar
Concentrator.
There are over 19,000 man-made satellites orbiting Earth right now, and half of these no longer function.
The issue of deep space satellites is that the further from the sun, the less solar energy. This means these satellites require much larger solar arrays, which is more expensive to produce and launch, and larger arrays have greater risk of damage by micrometeors.
Each satellite costs between several million and several billion dollars.
The reason it will stop functioning is that solar arrays normally lose efficiency over time and be unable to maintain the batteries at peak efficiency.
We have a solution, the Solar Concentrator.
The Solar Concentrator collects a very large amount of solar energy and concentrates it into a beam, which can be aimed at satellite from a great distance. Unlike normal solar energy, which reduces over distance due to the inverse square law, our device creates a solar beam that does not erode over distance.
Unlike a laser, which requires power to create the beam and is limited to a narrow band of energy, our device collects solar energy.
If the collection lens has a radius of 35 feet, then the area of this lens is 4,000 square feet, which is smaller than a lot of NASA's telescopes.
Incoming light is then concentrated into a beam of any diameter. If this diameter of the beam is set to 10 feet, then the cross-section of the beam is 80 square feet.
So 4,000 square feet of incoming light concentrated into a 10 feet wide beam is 4,000 divided by 80, meaning the beam is 50 times brighter than standard solar light that is not concentrated.
We can change how bright the beam is using a different size collection lens. We can also change the beam size by moving the concave lens closer to or further from the collection lens.
Suppose a solar array dropped to 10% efficiency. We can send to that satellite a beam that has 10 times more solar energy. So if the solar array is at 10% efficiency but gets 10 times as much solar energy, then it would generate the same full power of electricity. This means that the solar concentrator could make the satellites work far longer than designed, by us aiming these beams with greater concentrations of solar energy to compensate for the inefficiencies. We spoke with 6 optical and satellite engineers at NASA. They said that one of the reasons solar panels lose efficiency over time is exposure to infrared light. So we can put infrared filters in our concentrator so that the concentrated beam that hits the satellite has no infrared.
They said our device would work. There are many ways to keep the solar concentrator aimed at the sun, such as motors and gears timed with the Earth's rotation,
and photoreceptors that enable this to always stay aimed at the sun. Likewise, the reflection mirror can be controlled by gears to ensure the beam is always aimed at the satellites, and placing several of these devices around the globe so that one or more is always in the sun, or placing these devices at the north or south pole so that these devices are in the sun continuously for months at a time. This will increase the longevity of satellites, reduce the need to launch more to replace satellites that fail, and therefore reduce the amount of fuel burn, and reduce impact on the environment by decreasing the number of rockets launched to send new replacement satellites. We want to thank our school, the Schechter School of Long Island, our teacher, Ms. Lorber, SIGE, and Dr. Smallwood from SIGE for the support on this project. Thank you.